Hi, Brian Miller-Hicks here with my continuing Earth Science PowerPoints. We're up in space now. We're going to talk about planets, stars, and galaxies. As you know, we know a lot about space, much more than we did a century ago, but still a lot to learn. We've just started. So, how did we get here? What is in our solar system? Our solar system, of course, is that system of planets, asteroids, and moons orbiting around our own personal star, the Sun. The hypothesis for the formation of our solar system is that originally it was assembled from rocky, metallic, and icy debris, perhaps from the explosion of a supernova many billions of years ago. Estimated age of our solar system is about 4.7 billion years old. So it started out as a gas cloud, large cloud of gas, fragments of rock, metallic debris, gradually began to cool. As it was cooling, there's a rotational element imparted by the initial explosion of the star, perhaps a supernova. And a supernova, because it's an explosion of a very dense star, there's a wide range of elements contained within that star. As you will learn, a star is actually an element factory. Elements are made within stars. Okay, as the cloud continued to rotate, it gradually began to cool, although the center remained hot. The center remained hot enough to ignite into a star, another star, a new star. So if this is our sun, the material left rotating around the sun gradually accumulated as planetoids or planetesimals to eventually form our solar system. The makeup of our solar system is such that we occupy a special place in relation to our sun and in relation to other planets. That is called the solar habitable zone. In other words, not too cold, not too hot. That's why it's called the Goldilocks Zone. The position of the Earth relative to the sun and distance from the sun allows us to have water as gas, liquid, and ice, which is extremely important, of course, to the sustenance and perpetuation, survival of life. On a broader scale, there's also a galactic habitable zone. Our sun's right here. The center of our galaxy is here. And within this ring, we have our solar system. Let's start looking at the planets. Mercury in our solar system is closest to the sun. It is small. It's a little bit bigger than our moon. It's very dense. It's a rocky terrestrial planet. Because it's so close to the sun and so hot, there is no atmosphere that we know of. It has a large core, which is about 42% of its volume, 80% of its mass. Typically, a day on Mercury, the temperature would be 600 degrees centigrade to 800 degrees Fahrenheit. But there are temperature extremes. The side of Mercury facing towards the sun is as hot as 800 degrees Fahrenheit. Away from the sun, minus 170 degrees centigrade, or minus 173 degrees centigrade. Because there's no atmosphere, there are these very high range of temperature extremes. The surface of Mercury is quite cratered because it's been impacted by meteors meteorites throughout its history, and since it has no atmosphere to protect it, it's got a lot of craters in it. Okay. Next planet out from the sun is Venus, often called Earth's sister because it's very similar in size, although it's very different from the planet Earth. It's got an atmosphere, but it's 97% carbon dioxide. So Venus is a planet where the greenhouse effect has run wild. There's so much carbon dioxide in the atmosphere trapping heat that its surface temperatures are very, very hot, even hotter than Mercury, up to 900 degrees Fahrenheit. So that is an atmosphere. Hopefully we won't get to that point where we have so much CO2 in the atmosphere it traps heat to that extent. It has a lot of volcanoes on it. It's still an actively volcanic planet, perhaps, or perhaps these are ancient volcanoes. It has a bright surface. You can see Venus in the night sky. It's sometimes called the evening star, because of that blanket of carbon dioxide surrounding it, which is highly reflective. It reflects a lot of light from the sun. Let me go back a bit on the atmosphere of Venus. The actual reflectivity of the atmosphere reflecting light is actually due to the fact that the Venusian atmosphere has a lot of sulfuric acid droplets in it, which are highly reflective. Here on Earth, if we have volcanic eruption, a lot of sulfur is emitted into the atmosphere, combines with hydrogen, form H2S and sulfuric acid, which is highly reflective, and on Earth it can actually lead to a temporary cooling effect because of the sunlight reflection. And again, there are many volcanoes on Venus and relatively few craters because of the volcanic activity. Here's a shot of, or a computer graphic image of volcanoes of Venus. Mars, very, very intriguing planet. The red planet, our fascinating neighbor, fourth rock from the sun, if you will. There are many, many features on Mars which lead scientists to believe that perhaps there has been water on Mars in the past. Right now, it's very cold and dry planet. It does have polar ice caps, primarily of carbon dioxide ice, but there is water ice and water ice underneath the surface of Mars in some areas. Mars shows a history of volcanism. This area here is called the Tharsis Bulge. There's some major volcanoes here, including Olympus Mons, which is the largest known volcano in the solar system. If laid out on a map of the US, it would be about the size, the diameter of the volcano about the size of the state of Arizona, and about 3 times the height or the altitude or elevation of Everest. So it's a huge volcanic structure. Why? Well, plate tectonics doesn't seem to be operating on Mars. The origin or the creation of Olympus Mons is thought to be because it was sitting above a long-lasting hot spot which kept feeding magma to this volcano, and because there's no plate motion, the volcano just built up and built up and built up, got bigger and bigger and bigger over probably millions of years. This feature called Valles Marineris is the result, we think, of faulting. So there has been activity, volcanic activity on Mars in the past. We don't see much current activity. There is plenty of evidence for water on Mars. There are sand dunes, there are landslides. So it's a planet which is smaller than Earth, but it is a planet that many feel is a candidate for human colonization sometime in the future. I personally have my doubts, but the technology and the advancement of technology is such that it's possible, perhaps. My concerns are economic and the psychology of human beings. We'll see where it all ends up. As we know, we have been actively exploring Mars for decades. This is the latest robot rover that's on Mars, the Perseverance. This little aircraft here, sort of like a drone helicopter, is called Ingenuity, which is the first aircraft to fly under its own power on another planet. Here are the tracks of the rover Perseverance on the Mars landscape surface, which by all rights looks just like a desert landscape somewhere on Earth, perhaps Jordan or Saudi Arabia or the Sahara. It's quite an amazing planetary surface. Evidence of water on Mars, evidence of sedimentary rocks. These are layered sedimentary rocks, horizontally layered. And you can see here there's strong evidence for erosion, channeling of water. There's some sand dunes. So all in all, Mars is a fascinating place that we definitely want to explore further. Jupiter is a gas giant. It's one of the Jovian or gaseous planets, primarily helium, hydrogen. It perhaps has a rocky core deep in the interior and perhaps surrounded by solid metallic hydrogen. By the time you get close to the center of Jupiter, pressures are extremely great because it's such a huge, massive planet. It's the biggest planet in our solar system. The planet Jupiter has about 60 moons, including Europa, which is an ice planet, Io, which is Europa, which is an ice moon, Io, which is a very volcanically active moon, the most active volcanic body in our solar system, Callisto and Ganymede, among others. Now, because Jupiter is so big and there's so much internal heat, the internal heat is what drives these bands of storms on the planet's surface. Each of these wide bands that you see are bands of very rapid winds, perhaps up to 600 miles an hour. Winds in this band may be going the opposite direction of winds in this band. This large red feature here is the red spot, which is sort of a long-lasting giant cyclone or hurricane, which has been going on for centuries with wind speeds of huge force and speed, some up to 600 miles per hour, perhaps. Next up is Saturn, which is also a very large planet. But one of the interesting things about Saturn is its low density. If we could find an ocean big enough and we were to plop Saturn on top of that ocean, it would float. It's got an average density lower than water. Of course, all the gaseous planets are low density, while the rocky terrestrial planets are higher density. Saturn is interesting because of its rings. It has giant bright rings encircling it. In fact, all the gas planets, all the Jovian planets have rings, but Saturn has the most visible and most significant rings. The rings are made primarily of water ice, chunks of ice, interestingly enough. Next up in distance from Sun is the giant planet Uranus, the sideways planet, because instead of orbiting its axis around its orbital plane around the Sun, if you can imagine a marble rolling in a groove around the sun, that's how it rolls, more or less. So planet Earth, Mars, etc., revolve around their axes and revolve around the sun, whereas Uranus kind of rolls along its orbital plane around the sun. So sometime in the past it was knocked over on its side by some sort of immense gigantic collision. Now Uranus has this color because it's made of gases and ice gases. In other words, ice is made of methane and carbon dioxide, give it that color. Neptune, which is about the same size as Uranus, is called the windy planet because there are winds on the planet Neptune that can be 1,000 miles per hour or so. In fact, winds on Neptune can reach up to 1,500 miles per hour. It's got storm systems like Jupiter. That's what you see here in the Great Dark Spot. But these storm systems seem to last only a few days, whereas the storm systems on Jupiter's lasted centuries. So again, just like Uranus, we have a planet made of methane, methane ice, carbon dioxide, ammonia, primarily. Now, when our solar system was forming, a lot of the material became the sun and the planets. There was leftover stuff, debris, stuff that hasn't organized itself into planets. This material, a lot of it is in a band of fragments of rock and dust that compose a band between Mars and Jupiter, composed of asteroids, meteoroids. Comets is a whole other thing that I'll talk about in a minute. So here's that band of debris between Mars and Jupiter, the asteroid belt, fragments, rock, dust, etc. Millions of pieces of debris. Some of these asteroids lose their orbital energy and may head toward Earth and impact Earth. As we know, Earth has been impacted many times by meteorites or asteroids. For example, the Beheringer Crater in Arizona, the Chicxulub asteroid impact off the Yucatan, which is partly responsible for the extinction of dinosaurs some 65 million years ago. Here's Beheringer, or Meteor Crater in Arizona. This happened about 50,000 years ago by a fragment traveling 26,000 miles per hour, about a house-sized fragment that excavated this huge hole, which is about 600 feet deep and I think about 0.6 of a mile wide. So let me go back and talk about meteors, meteoroids, etc. A meteoroid is a fragment that enters the Earth's atmosphere. As it hits the Earth's atmosphere, it heats up due to friction with the air, becomes a meteor. If it actually lands on the Earth, it's called a meteorite. Here is a chunk of the iron meteorite that hit Meteor Crater. It's been excavated and it's on display. Comets, as I said, are a different animal. Comets have orbits that take them close to the sun and then far, far away from the sun. As they approach the sun, they get heated up, and the heat of the sun actually makes them sublimate gas, ionized gas. That's what you see here as a tail of a comet. That's gases that are being expelled from the comet by the sun's heat. Comet itself is made of ice, dust fragments, and gases. The dust tail is, of course, composed of dust. So the straight gas tail is pushed away from the sun by solar wind, and the somewhat curved dust tail, which is composed of dust riding along escaping gases, is pushed away by sunlight, which is a weaker pressure radiation. And these things can orbit for many, many miles outside the solar system, periodically come back. In fact, one of the most famous comets is called the Halley's Comet, and it returns to us every so often. Let's talk about stars and stellar evolution. What is stellar evolution? Stellar evolution is the life and death of a star. A star, of course, is a burning sphere of gas. Our sun is a star. Stars come in different sizes, different colors, different intensities, different brightnesses, and different lifespans. So this is a diagram called the Hertzsprung-Russell diagram, HR diagram. It's organized by surface temperature down here, by absolute magnitude and luminosity or brightness. So stars up here are very bright and actually lower temperature. So the brighter stars may actually have lower temperature. The higher temperature stars have, the higher temperature stars over here actually are of lower luminosity or brightness. So we have white dwarfs, which are dim but hot. We have red supergiants, which are bright but less hot. I mean, everything's pretty hot, but these are lower temperature than these. We have a band running through the middle, more or less, and our sun is right here. It's an average yellow star, pretty much middle of the road temperature, middle of the road brightness. Okay. Most stars are in this band called the main sequence. Stellar evolution in this graphic is easy to grasp. You start out with a nebula or a gas cloud, which is actually formed from the explosion of another star. So the destruction or explosion of a star can lead to the birth of a new star. Okay, so this nebula cloud of gas and dust forms a protostar, which condenses into a main sequence star like our sun. The lifetime of our sun is around 11 billion years or so. We're about halfway through, so we've got another 5 billion years to go before it turns into a red giant, which will expand in our solar system to eventually engulf us because of its huge size. Now, we still got 5 billion years, so we still have time to pack and leave. This red giant will eventually shed as it runs out of hydrogen fuel. The reason why a star dies is because a star burns up its fuel, its hydrogen. Hydrogen turns to helium, but when there's no more hydrogen left, the inner gas pressures will overcome the gravitational pressures. The star will swell and become, in this case, another nebula, and the center, the remnant star, will become a white dwarf, a hot, dim star. If we start out with a larger star, this can become a red supergiant, which, because of its mass and massive size, can explode into a supernova. Supernova explosion, which results in the expulsion of huge quantities of gas, dust, etc. The remnant of a supernova can be a neutron star, or it can even be a black hole if it's small enough and dense. So to summarize briefly again, the life cycle of a star is composed of hydrogen gas, which burns into helium. As the hydrogen is depleted, the star will contract. Then the helium burning becomes more intense, increasing the gas pressure and energy. The star balloons outward until it starts casting off, shedding shells of gas. It either becomes a nebula, or if the pressure of the energy being produced by intense hydrogen burning in the center is so great that it explodes in a giant supernova explosion. So all through its life, there's a battle between gas pressure from burning hydrogen and gravity, which wants to compress the star. Stars cluster together into galaxies, which are composed of billions, millions, and billions of stars. This is what we conceive of as our own Milky Way galaxy, which is a spiral galaxy, which means it has spiraling arms as the galaxy rotates around its center. Now we arrive at the concept known as the Big Bang. The Big Bang is a popular phrase which denotes the supposed hypothesized origin of our universe, that it started from an infinitely dense, small point of matter, which was at a point where it had so much energy contained with it that it exploded in a disastrous, large, I shouldn't say disastrous, in a huge explosion. There is evidence for this that is denoted. We have actually been able to detect what's called cosmic microwave background radiation from this initial explosion. And the reason why I'm showing you this electromagnetic spectrum is to talk about the red shift and the blue shift. An astronomer named Edwin Hubble in the 1920s discovered this effect. He was looking through his telescopes and noticed that when he looked at galaxies far, far away, he noticed they had a red cast to them. Now red, the red end of the visible light spectrum, means the wavelengths are longer. The blue end of the spectrum means wavelengths are shorter. Well, why would distant galaxies have sort of a long red wavelength to them? And Mr. Hubble surmised that that's because these galaxies are moving away from us. And the red color has to do with something called the Doppler Effect. If you look at this graphic, as you have an ambulance with its emitting its sound waves from its siren as it's approaching you, the wavelengths are being compressed. The sound wavelengths are being compressed. As it's moving away from you, the sound wavelengths are being lengthened. This is the same effect that happens with light waves as with sound waves. As an object is moving rapidly away from you, the wavelengths of light are actually becoming longer, which shifts the light towards the long end of the spectrum, or the red color end of the spectrum. So that's why Mr. Hubble was able to detect a shift in light waves toward longer wavelengths and a redder color. That means the galaxies and stars are all moving away from us at a very fast rate, which leads to the concept of an expanding universe, and that fits well into the theory of a Big Bang where an explosion occurred and everything is now racing outwards. We don't know if this will continue to happen, or we don't know if the universe is going to shrink back, or perhaps shrink back and then bounce outwards again. That's all still to be discovered, and evidence needs to be brought forward for any of these scenarios. So the expanding universe is our current model, very simple model of a rising lump of dough. Here's a raisin bread dough before it rises, and as it rises or expands, in this case from heat, Each raisin, which was now 2 centimeters away here, is now 6 centimeters away. 5 centimeters here, now 15 centimeters away. So every point in this expanding dough, in this expanding universe, is moving away from every other point. So that's a very short summary of a complicated theory or set of evidence. We're continuing to learn about it. Mr. Einstein helped us figure out a lot of this stuff through his theory of relativity, his prediction of black holes and gravity waves and other phenomena. So again, we know a lot, but there's still a long, long ways to go.